Cool. So in this lecture, I want to go over a very common problem in multi-threading called an atomic FIFO. So you may have this situation, and this is honestly extremely popular in operating systems. Let me quickly adjust this. So you may have some sort of producer on one side that maybe is running at a different speed than some sort of consumer. And a basic example would be maybe like a computer mouse. So a computer mouse, so as you move around the mouse, what will happen is you will be sending basically just like a list of integers of the current like mouse like position and movement. The little like sensor inside of it, maybe it's sending off like little beams. Maybe there's some sort of trigonometry or something that needs to be run in order to figure out exactly where the mouse is on the table. But all the mouse does is maybe it just produces a bunch of integers. And so these integers, so let's say that this is the mouse. And so maybe the mouse will fill up now, it will fill up some sort of FIFO depending on the current like whenever you wiggle the mouse, maybe that pushes something onto this FIFO. And then maybe your consumer is a CPU, and maybe the CPU doesn't need to pull the mouse too often. Maybe it pulls the mouse like at 60 frames per second or something, but maybe the mouse is operating at like 1,000 inputs per second. These are totally reasonable scales to deal with. So yeah, so if the mouse is generating like 1,000 numbers per second, but the consumer like doesn't need to be processing all that faster than just like 60 times per second, then what would happen is the mouse would probably need to like slow down in order to now match the CPU speed. Because if the mouse wanted to send out like 1,000 integers, it wants to make sure that the computer actually gets all 1,000 of those integers. So what a common solution is we have some sort of buffer in between them. And this buffer will fill up, it'll fill up, it'll fill up, maybe it'll fill up with like, yeah, maybe 1,000 entries. And then when the CPU is finally ready, when it finally has time, then it can go and it can process all 1,000 of these entries. And CPUs, they will run at a few gigahertz. So yeah, it can process all this in just a microsecond or so. But yeah, what's important is the mouse does not need to wait for the eventual time when the CPU is actually ready. So this is a very common problem. Yeah, FIFOs, they are super useful, especially in just like low level devices and anytime where you need to send large amounts of data from one producer into some consumer. Yeah, and you could also have the potential where you have maybe um, multiple producers. So maybe you have a mouse, maybe you also have a keyboard or something. Maybe you have some other sort of producer here. Maybe, I don't know, whatever. Maybe like a game controller or something. So I'll call this X input for like Xbox input. This is the Microsoft controller standard. And yeah, so maybe all of these are sending some sort of packet, and this packet is maybe like, hey, I am a keyboard and I'm pressing this button or something. And so what will need to happen is maybe you have a CPU now that needs to process this. Or maybe now you have actually like multiple things that are processing this. And let's assume that each one of these kind of drivers, each one of these things that process the incoming data and then add it to the kernel space, so that the driver, let's say that each one of these runs on a disjoint thread. This is totally reasonable. And what we now need to make sure is that we don't have any collisions, and we don't have any race conditions inside of this FIFO data structure. And this is a non-trivial task, but it's something that I think it would be very important if we went over today. It's overall not too complicated once you see the solution. So, okay. And if we start even just a little bit simpler on this, so going back to just like the mouse and just the mouse and CPU example. So the biggest kind of problem with this is that, well, yeah, so we're not going to have any race conditions between different human interface devices. But maybe what we do have is the mouse will try to push something onto this FIFO at the exact same time that the CPU tries to pull it off of the FIFO. So maybe at the mouse, let's say at the moment the FIFO has the values like 1, 2, and 3. And then boom, at the exact same moment, maybe on two separate cores, maybe now the CPU pulls out this first number and starts processing it, and then the data slides over. But then at the exact same moment, now the mouse sends over the next bit of data. And maybe if they happen at the exact same moment, then now that introduces some race condition where maybe not all of the data was able to slide over because it expected now that there was going to be some, it expected both a push and the pop at the same time. So okay, let's take a look at what this would look like now in C code. So I actually do have a basic kind of implementation of this. At the moment, it is unsafe, full of race conditions, but let's take a look at it. So here I have my atomic FIFO class, and all it is it's just a wrapper around stdq. And so here I just have a push method. What the push method does is it just calls the queue push, and then it also prints out this little message right here. And then the pop method, what it does is first it checks like, does the queue actually have any elements for me to pop off? If it does not, then go and throw an error. But then it goes and pops off the message. Then it prints out. It pops out the front of the line, and then it prints out the message. Cool. And then if we look at our main function, that you can think of this as just like a test case that we want to verify our atomic FIFO works for. So here I have a producer function and a consumer function. And yes, you can see the producer, it just pushes some random value onto this queue, and then the consumer function will just pull the item off of the queue. And what we have here is we have 100 different producers. So you can imagine that the FIFO is going to fill up with 100 elements, and then we are going to consume all 100 elements. So we should see that, it fills up and then it goes away. So you will notice though these are all threads. So actually all of the 100 things are going to try to happen all at once. They're all going to be try to be added to the queue at the exact same time, and all of these things are going to be tried to be removed from the queue at all the same time. So we're going to have a lot of contention, a lot of race condition issues here. So okay, let's just see what happens though. So if I cd into queue, I've already compiled it, so I can just run /main, and oh, good. Okay, actually, it looks like it worked perfectly. Okay. Okay. Actually, this is a little bit weird. It looks like it popped to 0, even though I wouldn't really imagine it to ever be able to come up with the value 0. That would be like a 1 in like a million chance. So that's probably a bug. We can scroll around and we can see, okay, cool. So it actually was able to push all 100 items. And even though all of these threads are all technically like abstractly running in parallel, the operating system actually looks like it ran most of these just exactly sequentially. We can try to see if there's any reordering. Oh, okay, actually, yeah. So it reordered at first. So we push the 6th element, then the 4th element, then the 1st element. But then after that, it looks pretty good. 13, 14, 15, 16, 17. So for the most part, the operating system chose to run most of these threads just sequentially, but occasionally it does like a reordering. And then we can see, it then pushes element 100, and then it starts popping everything after that. Cool. Okay. So that's kind of the deal with race conditions, right? Is that they don't always show themselves. So what I actually will do instead is I'm going to run /main in this while loop right here, and this will just repeat until eventually it fails. So okay, let's see what happens. So if I hit enter, okay, actually that failed really quickly. Sometimes it takes a while. Let me see what happened. Okay, this is kind of weird. So it says out of range, right? This is odd because like we pushed 100 items to the stack, and then we pulled 100 items off the stack. So in theory, we shouldn't have any issues. But if we scroll up, then maybe we'll see something that makes sense. So okay, well it looks like so we pushed item 99 but actually it looks like we never even pushed item 100. And if we scroll up, let's see if we can find out why. Oh, actually, this is weird. So look at this. It looks like we pushed item 74 two times in a row. So it looks like there's some sort of race condition here where we actually screwed up the implementation of this queue function. Maybe it interleaved the instructions, the assembly instructions in some way that now it pushed element 74 twice, and so it probably overrode this first value. In fact, I wonder if what would happen if we searched for this. Will it show up? Actually, it shows up because um, that that is actually interesting that it shows up. Okay, let's double check. So, okay, what if does this one show up? Let's see. Okay. Actually, look at this. It looks like this one does not show up. It shows up in previous runs because I've actually run this example a couple times. But if we scroll down to like the pop section, we can see that it actually never ends up popping this element because we overrode it, and that is why it tries running pop even though eventually the size became 0. So okay, therefore what we have is the producer threads are interfering with one another. Okay. The solution to this, of course, is if you remember from the previous lecture, is we actually need to add a mutex here. So the point of a mutex, if you remember, it's kind of like a bathroom door. You can think that like when someone wants to use this atomic FIFO class, what they need to do is they need to check like, is the bathroom door locked? And if it is locked, then I need to like wait my turn. But if it's not locked, then I can go inside the bathroom and I can immediately lock the door behind me. And then I can do whatever sort of push and pop operations I need to. So let's go and do that. So I'm going to create a mutex. And yeah, we'll just call this lock, I guess. Good. And now I can utilize this and I can put this in my push method, and I can call lock on this. Good. And then I can call unlock on this. It's always very important to unlock all of your locks once you're done with them, or else you have something called a deadlock where a lock will never reopen. Okay, but now let's do the same thing just up here. Good. Okay, cool. Notice that I'm calling unlock before return. Yeah, that's very important. If I did this, then we would never unlock. So, okay, cool. Let's go and see if that fixes it. So if I now go and compile this, okay, I just need to include mutex, I believe. Mutex, and yes, it looks like, oh, good. Oh, okay, it looks like we're still getting an error, which is unfortunate, but, oh, okay, hold on, let me restart this. Okay, so cdq. Okay, let's double check. So if I just do /main, oh, actually, okay, so it looks like it worked. But we did see it did fail. If I run this over and over, we can see that it, for the most part, seems like it's working. That's actually super rare that we got that issue. But you may guess that there is actually still a race condition in this. Now, it's a very rare race condition. It looks extremely rare. But let's see what happens when we do our while loop again and see if we can uncover this race condition again. So I'm going to run this, and it might take a minute. But oh, okay, cool. So we got this race condition error. Let's see if we can figure out what the issue is. So okay, it looks like we push an element. Well, so look at this. So we're in like the popped section, but it chose to actually reorder a pushed function right here. And if we scroll it more, oh, we can see that actually some of the pushes are getting like kind of like pushed into the pop section. So my guess, if I like scroll up more, I'm guessing what we have is maybe we are not actually pushing all 100 items before we run all of our pop. So what we have is like the consumer is reading this FIFO. It's reading. It's expecting there to be data. And 99.9% of the time there is data there. But every once in a while there is not data there. And what we have is we say like, oh, if there's not data, then throw an error. But that's not what we want to have happen. Instead, what we probably want, this is kind of crazy, but what we probably want is if there's no data, instead of throwing an error, we actually probably want to just wait until there is data. Because, yeah, like if there's going to be a future producer, then we need to make sure that we account for that. So, okay, let me go and modify this now to double check that, yeah, so now instead of just throwing this error, now we can just kind of context switch away until eventually a producer does come back. So okay, let's see if we can figure this out. So here, yeah, so we're locking, and that's good. But then we say like, oh, so if Q is empty, then what we should probably do is unlock, okay? Yeah, so what we should do is probably unlock this. Okay, and then we can, maybe if we want, we could sleep for a little bit. So we could do, I have it written down. It's kind of a long command, but, or a long function. But so we can do std this thread sleep for, and then we can sleep for some number of milliseconds. And 10 milliseconds, that's totally reasonable. So now we can sleep for a certain amount. Then if we want, we can go and lock it again. And then at this point, now we could go and continue with our function. And so this should probably work now. Let's double check. Okay, so if we do G++, okay, oh, what's going, oh, I need to now include thread. Okay, good. Oh, good, okay, so if I now run this, then okay, we can see that things are looking pretty good. Now you may still be screaming at your screen for a little bit because this is not going to work for every test case, right? Because we're sleeping for 10 milliseconds, and in this case, that works perfectly fine. But what happens now if our producer maybe is like, maybe this is a very complicated sort of task that we need to run, and maybe, and I'll just kind of model this as a sleep, maybe this task needs to run for like 100 milliseconds in order to do this big hefty computation, and then finally then we go and push the FIFO on. So now let's see what happens. So if I now go and compile this and run this, okay, well it looks like it worked, but now watch what happens when I run this. Okay, you can see, well, actually, it doesn't look very good, right? It looks like, look at this. Okay, so it looks like we still have some sort of issue, right? And that means popping 0. Oh yeah, and then it goes and pushes all the stuff. So okay, we're not quite where we want. Yeah, okay. So yeah, you know, and that's probably because we're sleeping for 100 milliseconds here, but here we're only sleeping for 10, so it's immediately locking, but it's not actually rechecking this like is empty. Okay, yeah, so now we should have maybe like another if statement that's like if is empty again, then now go and, well, honestly, like if it's empty, then we should unlock and we should sleep again. So actually, this is more looking like a while loop. So maybe instead of this, we could just have like a while true. So we could say while true, and maybe we say so lock, and then we have if empty. So if, yeah, if it's empty, then go and unlock the queue, and yeah, and maybe sleep for a bit. But if it's not empty, yeah, but if it's not empty, so I'll say else break. And what this will let us do is, yeah, is now if we lock this so nothing else can touch it, and then we notice that it is not empty, that means that now we can break out of this check, and then now we can perform the pop like usual. But if we notice that it is empty, then we will unlock and we will sleep for a bit, and then we will lock again and then check for empty again. So okay, now let's go and test this. So in theory, this should be good now. So if I go and run this, okay, you know, it's a little bit hard to tell. And and this is the whole thing about race conditions is it's really hard to actually tell whether your code is working. It looks like it's working at this point, but it's a little hard to tell. I will tell you though that this code should be good now. I personally do not see any more places where there could be a race condition. So I think we could leave this code running for like forever, and it should never fail unless maybe some like hardware failure happens where like a transistor like flips when it wasn't supposed to. So yeah, there we go. This sort of structure is what you should probably kind of do anytime that you need to check something before you actually acquire a lock. And this is kind of leading into a different topic, which I will not talk about in this lecture. But this new topic is called a condition variable. So what a condition variable is it's when a lock is unlocked when a condition is true. Or So actually, wait, sorry. It is when a lock is taken when a condition is true. So you could imagine, like in the bathroom analogy, maybe someone is waiting for the condition for there to be soap or something, or maybe someone's waiting for the condition for them to actually need to use the bathroom or something. So maybe they're all waiting in line and they're not going in line yet until a specific variable like changes, until a condition changes, and then that specific thread is now okay to go into the bathroom. And in that time when that thread is waiting, like in this time when I'm currently like I'm checking like, oh, like is queue empty? Like if it is empty, let me just wait. In this time, other threads are allowed to go into the bathroom and they're allowed to use this lock. But yeah, that's what's so great. It's like you can see this lock, this unlock is actually directly followed by this sleep for function. And yeah, so this sleep for will allow all the other threads to come in and use this data. So there we go. That is kind of the whole idea with this with the atomic FIFO class here. You will undoubtedly need to implement this probably several times in your life. Yeah, the idea of having a like a condition variable type structure here where we need to check whether or not we can actually take a lock, and then also yeah, putting locks around accessing a queue or really just accessing any sort of data. So there we go. Hope this was illuminating, and yeah, now gives you some background if you ever need to perform this type of problem before.